Hello, and today we're going to do a Let's Play of TIS 100. This is a Zachtronics game, which means it's going to be nerdy as all get out. This is sort of the predecessor to Zachtronics Shenzhen I, which we've also done a Let's Play of. And this is a game that simulates writing assembly language on a computer with a very strange architecture. In particular, the manual sets out the premise that we've inherited this computer from our Uncle Randy. And the manual explains a lot about the architecture, and in particular is going to tell you the various opcodes you need in order to play the game. This is a game where reading the manual is not at all optional. So keep that in mind. So let's launch it here. Uh-oh, there's some corrupted segments. So here we are, and what we can see is we have this segment map. We have a specification editor, which will let us make our own puzzles if we want. But for right now, the only thing that's unlocked is this self-test diagnostic. And over on the left here, we have statistics that are going to show us how well or how poorly we do in relation to all of my friends. And I'm sure this is going to be a really embarrassing situation as I manage to create less efficient solutions than all of them. So let's go ahead and do the self-test. All right, so this is the TIS screen. The concept here is that each of these small boxes in the main area are separate CPUs. You can see that there are arrows leading into and out of those boxes. The object of the game is to win. You win by giving the correct output to the out.x output, which is just to the right of the fast forward button on the bottom. These nodes that are in red are broken and you can't move data into or out of them. Some of the nodes, like this one on the right-hand side of the screen, have this button that says debug. And if you click debug, what happens is you get to look at some of the memory that your Uncle Randy, some of the things that he had written. And so here it talks about him finding this weird machine, and he has no idea who made it. And this is how Zachtronics keeps this from being a pure puzzle game. They introduce plot through these little snippets. Okay, so up in the upper left, we get the goal for this level. Read a value from in.x and write the value to out.x. And read a value from in.a, which is over here on the right, and write the value to out.a. So if you look here, you can see that they've already filled in the in.x solution to us. And indeed, if we run this program, all of our out.x values are correct. The expected values match, but of course that's not true for out.a. So how do we do this? Well, we can go to the manual and we can ask ourselves, well, what are the commands that we have to work with? These are the various ports that we could use. We have an accumulator. We have a backup, which is temporary storage for the accumulator. We have nil, which is black holing things. We have ports, which are left, right, up, and down. We also have some pseudo ports, any and last. And then we have an instruction set. The instruction set has comments, it has labels, it has a no operation instruction. And for this puzzle, I think all we're going to need is this move instruction, which moves a value from source to destination. So let's get rid of our manual here. And you're going to hear me clicking and typing. So we're coming from in.a, which is the up port. And we'd like to move it down to out.a, which is below us. But of course, we have this broken node in the middle, so we're going to have to route around it. Move right down, move up, down. You can see that if we type something that isn't an opcode, it will tell us. We can put labels. right. Obviously, we don't need this label here in this case. And move left down. Pretty simple. Let's run and see if we got it right. Oh, actually, before we do this, let me just show that you could step through this. So rather than just running, I'm going to step. And you can see that the first value up here in the upper right is 68. It's going to move into the first mode and immediately out of the first node to the left. And then it's going to progress through the system until it reaches the output port, at which point we see that under out.a in our test output, we've gotten the correct value. So we're going to run. It's going to run a few sets of tests. And we've succeeded. And for perhaps the only time in this Let's Play, you'll see that I got the same results as everyone else. So we can keep editing, but obviously there's not a lot to do here. We'll return to the segment list. Great. So now we've unlocked another puzzle. So let's go ahead and jump right into it. Signal amplifier, create new program. What are we supposed to do here? We're going to read a value from in.a. We're going to double the value, and then we're going to write the value to out.a. Okay, so how are we going to double the value? I can think of two ways to do it off the hands. We could do some math. Let's see. There is, let me bring the manual up here so you can see it. There is an add function, so that might be the simplest way to do it. We have some flow control, jumping. We could try and do this with, say, 2 moves somehow. But I think just doing this in the most straightforward way is probably the best thing. So let's go ahead. So let's say we're going to do all our work right here. I'll put a comment there just so we can see how that goes. We're going to move this here. We're going to move this here. All right. So what we're going to do is we're going to say, instead of moving to the right, we're going to put this in the accumulator, which is one of our registers. And then we're going to, let's see, add says the description of source is added to the value of accumulator and the result is stored to accumulator. So I think add ACC should make this happen. We shouldn't need to clear the accumulator because we're going to move a value into it. And then we could say, move that to the right. I don't know if this comma is strictly necessary. Let's say that it is. All right, moment of truth. Well, let's step through again. We're getting a value, 66. It's coming in. It moves to the second CPU. It moves into the third CPU, which puts it into the accumulator and then adds it to itself and then sends it to the right and then sends it to out. And that looks like it's working. Let's take a look. Let's see if someone came up with a more efficient solution than this. If this goes too slowly, you can click the fast button. All right, we can see that we used twice as many cycles as all of my friends. They will love to make fun of me about this. So at this point, normally if I was playing for myself, I would probably stop and I would say, oh, I'm going to go back and I'm going to edit this again and really work on optimizing it. But for right now, let's just, oh, you know what? Let's do that. Why not? Okay, so what's going on here? Well, the thing that jumps out at me is this is a multi-core architecture, right? And we have all of these cores that are currently not being used. So what if we tried to speed this up by using multiple cores? Let's take a look. Let's do the math here. And we can copy and paste here. And yes, that's going to the right, so that's correct. And then here what we'll do is we'll use this any pseudo port, which any should, I believe, just read from whichever port has data. I hope that's okay. And now we're going to move from up. Well, I'm not sure this is going to work. Let's find out if it does. Well, that looks visually as if it's going a lot faster. And, oh great, now we're matching our friends. And I noticed that there was a little more plot here where our uncle is saying that it seems really confusing. It seems like something they'd come up with in the USSR, but why is the manual in English? Why indeed, dead uncle? All right, so now, having done that puzzle, we've got 3 more opening up. I'm not sure how long I want to make this Let's Play today. I'm not going to go through the entire game. No one wants to sit here and watch me play for 6 hours. And I'm probably at this point going to stop trying to optimize any of these. Let's just go on to the next one and see how hard it is. One thing to note here in the upper left, the game does give you multiple slots for each puzzle. So if you want to try different techniques, you can go ahead and give that a go. So what's this puzzle? Read values from A and B. I'm going to stop saying in.A and in.B. Write A minus B to out P. Write B minus A to N. Oh, we got a plot note here. We got to read that. There's some sort of static memory. Okay. So let's look at this first value. A is 44 and B is 93. And so P is going to be A minus B, which is negative 49. And N is going to be B minus A, which is 93 minus 44 is 49. Well, looking at the manual, we see that there is a subtract opcode. There's also a negative opcode. The value of the accumulator is arithmetically negated. A value of 0 remains the same. And looking at the outputs, it sure looks like all of these outputs are each other's, the negative of each other. So one way we could do this would be to try and do both subtractions. That seems kind of confusing to me. So let's see, which one of these would be easier to do? Let's say we're going to do A minus B. So we'll do all this right here at the top, which might be a mistake. Now we're going to move right. No. I guess with subtraction, the value of source is subtracted from the value of accumulator. So if this needs to be A minus B, we do want to move this into the accumulator, and then we want to subtract from the right. And then we want to move the accumulator down. This wants to move up into the accumulator. Oh, and then we want to move the accumulator down, negate it, and move the accumulator. I want to do this actually here. No, you know what? I'm not sure where this is better to do it. The question is, am I going to stall things more? It probably doesn't matter. It probably ends up being the same, but I'll do it in this middle node for simplicity. Down, move up, down. This up here needs to be moved from up to left. Okay, and this needs to be moved from up to down. Is that it? So data is going to come in here, be subtracted. The result goes here. The result continues on down through the bottom You can't see my mouse pointer. It just occurred to me, so it sounds like I'm a crazy person talking to us. Oh, let's step through and watch it. Here come our first values, 44 and 93. 44 is in the accumulator. We end up with negative 49, which is the p-value. That goes down, continues down, is negated, goes to the right, goes to the down, and that looks correct. So let's run it. That's looking awfully slow. I predict I'm going to be slower than my friends here. I love watching this stuff step through. I know it's a pointless animation, but I could just watch it for tens of minutes, and have, when the program gets sufficiently complex. All right, so where'd we come in? Once again, we are the slowest. That doesn't surprise me. We also used more nodes than our friends, and we used more instructions. Well, I'm not going to try to optimize the cycle count, but I am going to optimize the nodes. I think we can get rid of this node next to the communication failure node. That one can go away. This becomes up and down, and then this becomes left and down. I don't think this is actually any faster. I'm going to run fast here. Okay, so our time, a cycle count, is exactly the same, but we have improved our node count and instruction count statistics. One thing to note here, you don't have to solve you don't have to optimize all three of these axes at the same time. It's perfectly valid, and in some cases required, to create different solutions to optimize on different aspects, just like in real life programming. Return to the segment list. So a question I get a lot is, when talking about these games, is how much like real assembly language is this? It's not a lot like real assembly language. There are some aspects of it. I'm going to go into the next program here. There are some aspects that are similar. Certainly, the micromanagement of where your data is coming from and going to is similar to assembly language, but the restrictions on where data comes from and goes to, and particularly the amount of space you have here, is really, really small. And so if you, let's see, how many lines is this? You use up all those lines, your program is done at that point. You cannot add anything else in that CPU. And that restriction in particular, even in the days of 8-bit computers and machines with 4K of RAM, you had more than about 20 or 23 lines to work with. So this is fundamentally still a game. If you're really good at TIS 100, that doesn't mean you're really good at assembly language, but it does put you into the mindset. So let's get rid of that. I see there's another debug mode, and we see that Uncle Richard is complaining a little bit. Uncle Ray, I think was his name. No, I don't remember. I say the bottom's going to drop out of the microcomputer market soon. Mark my words. All right, so what's going on here? Read a value from n. Write 1 to g if n is greater than 0. Write 1 to e if n is equal to 0. And write 1 to l if n is less than 0. When a 1 is not written to an output, write a 0 instead. So they want us to implement flags here. And we can see that because of the arrangement of broken nodes, and this is what I mean when I say the game is very puzzle-like, we're going to have to traverse these 3 out nodes for every value. So the absolute minimum number of nodes for this puzzle, for us to solve it efficiently, 1, 2, 3, 4, 5, 6, it's going to be 6 nodes. And even in the case where something is greater than, we're still going to have to touch the other nodes. So this looks, I don't know, I always begin these puzzles saying this looks simple and then end up struggling with them. So let's go there. So I don't think we could really do any, I don't know. We could do something in these three nodes, I guess, where we ended up creating some flag here, which then simply was decomposed in these three. But let's take a naive solution first. So we're going to say move left to accumulator. And the point of this puzzle, I believe, is that we're going to have to start using some of these conditionals. So let's look at a sample conditional. For this greater than, we've got section 213, JGZ, transfer execution conditionally. The instruction after the label will be executed next if the value of the accumulator is positive, greater than 0. Okay. So what do we got? So we want if it's greater than 0. So let's just do that. Let's say if it's greater than 0, we want to go to some label. Let's say true. And it's telling us now that the label's undefined. That's fine. I'm going to use another label here. I'm going to use S for start. So if we're greater than 0, we're going to jump here. And we're going to say, you could do this, by the way, on one line if it will fit. If it won't fit, you can put it here. We're going to say move 1 down. And the nature of these nodes, I don't think I said this, is if it reaches the last line of execution, it implicitly will jump back to the first line of execution. So it's not going to halt or anything at the end unless we tell it to. But if we did not jump, then we want to move 0 to down. Otherwise, we're going to jump unconditionally back to S. And you know what? Let's put that label on a separate line. And we could even give it more. There we go. Now this actually is not good enough because we do need to trigger the remaining nodes. So instead of going to start, we'll jump to continue. And we will then move our value in the accumulator off to the right. And now our start label is unnecessary, so let's get rid of that. I think that's correct. So this one is if our value is equal to 0, and there is this JEZ, which is the opcode we want to use. So for this node, I believe that our instruction, our program is basically exactly the same. And then for this node, for this one, we don't need to trigger to the right. So we're just going to do jump of less than 0. And in this case, we are going to use a start label. I could swear the game was indenting for me in some previous run, and I don't see it doing it now. I'm not sure why that is. I might be getting confused because there's actually an iPad version of this game, which is amazing because it has this beautiful retro keyboard, and I highly recommend it. I think that's it. So before we run, where's the inefficiency here? I feel like there might be something clever we could do. You could see we have separate move instructions for 0 and 1, and there might be something clever we could do to make that tighter, but I'm not going to worry about it. Let's do a one step through here and make sure that it all works. So we're getting 2 as our value. It's coming to the first node, moving through the nodes, gets to the greater than node. 2 is greater than 0, so we expect to jump down there. We do. And then we're sending it on to the next one. We expect this one to output a 0, which it does. triggers the next node. We expect this to output a 0, which it does. Let's see. Okay, I'm not going to make you watch this, even though I love it. I'll go fast. Not too bad. We are again the slowest. You know, that's my idiom. We also used more instructions than the best people, but we did I think kind of hit the average there. So let's return to the segment list. All right, I think maybe I'm going to do one more, and then I will call this finished. Read values from A and B. Read a value from S. When S is -1, write the A value. When S is 1, write the B value. And when it's 0, oh, you when it's 0, write A plus B. I was starting off like, oh, this is easy. It's just a mux. Gentle reader, it's not a mux. Okay. Now, the one thing that jumps out at me here is there sure are a lot of open nodes, which reads like it's almost encouraging you to do something clever with this A plus B. So thinking out loud how I would optimize this in the abstract, what I would probably do is unconditionally always compute A plus B in one of these nodes somewhere, and then just use the value if it were needed. Not sure if that's going to be the right thing to do. I could also see that leading to deadlocks. Well, while we think about it, let's look at this node. Oh, he thinks he knows where it came from. And it's some sort of secret government project, something the CIA cooked up to comb through Soviet radio signals. The plot thickens. Is it a classified device? All right, so let's, again, just approach this as naively as possible, right? So the tricky bit here, though, is that S is essentially a trinary value, isn't it? You know what? Let's put all the logic right here in this first S node, which is probably a bad idea. Might not even fit. I don't know if I could fit it into these lines, but we will see if we can do it. Let's see. I already see where the complexity is going to be here. So we're going to move up to the accumulator. We'll go ahead and put a start label here because we're going to need it no matter what. And we're going to check if it's 0. 0 is the bad case, right? So if 0 is in the accumulator, jump to the hard case. Let's go ahead and figure that out now. If 0 is in the accumulator, we're going to add left to right. I'm out of space. This is one of the most annoying things about this game. A lot of the Zachtronics games, especially the earlier ones, limit the amount of space you have to work with. It's a very artificial constraint, and I don't like it. In fact, what I consider to be one of their best recent games, Opus Magnum, was basically a reworking of Space Chem, but giving you an infinite grid or an infinite hex grid to work with. All right, so in that case, we're going to add left to right, and we're going to, oh, that doesn't work. Okay, why not? We're going to move left to the accumulator. We're going to add it to right. We're going to move the accumulator down. And in that case, we are done. So that's good. So now we need our quote unquote easy cases. So we know that the last thing we're going to have to do is short circuit the hard case so that we don't do that. So we need to see, are we less than 0? So if we're less than 0, we're going to take the left case. So let's call that label L. We're going to say L is move left down. And it's going to throw away the right value in that case. I believe that's what why do we have to throw away the value explicitly? Because these values move through these channels like pipes. And if we don't do something with the value being vended to us, it will block the pipe. And then in this case, the B input would just sit there forever. And we wouldn't actually be able to get the next value along the way. Move right to nil, and then in that case jump back to the beginning. I believe that's correct. And lastly, we need to fill in this bit here, which is move right down, move left nil. All right, I feel pretty good about that. I'm not positive it's correct, but hopefully it's at least an approximation. All right, and then all of this is just plumbing. And what you're seeing here, the way I'm doing this, is very much my failure mode for this game. I tend to go for the simplest solution first, which means that I kind of throw away all the advantages one could get from parallelization. Let's see how it goes. Let's do a step through. Okay, our first 3 nodes run. They start feeding their values in. This is going to be we want the value from the left, which is 13. We are indeed... Oh, I already see a bug. Sorry. I forgot to do this. Okay, let's try that again. Okay, we are indeed sending negative 13 down. Now we're doing one from the right. And that one's okay. Have we got a 0? This is our 0 coming in here. It looks like it's doing the addition. Yeah, that looks okay. Let me show you. I realize I have not shown you what an error looks like. So let's intentionally break this. And I'll show you 2 failure modes, and then I'm going to call this Let's Play done. So first, let's just show you what happens when you give the wrong answer. You get lots of beeps, and in this case you'll note that it only goes through one screen of tests. If you have any errors at all, it tells you to try again. All right, so let's reverse that. And now let's show you another failure. Let me show you the pipe failure. So to simulate a pipe failure, what I can do is comment out this line here. Let's try it again. Yeah, and now you can see the idle count on the CPU is growing. We are theoretically running, cycles are going, but nothing's happening because I've backed up all the data. All right, so now let's run it. We'll do a fast run just to get through this. There we go. Hey, I'm not the slowest. Close to the slowest, but not. I feel very proud of myself. That's an achievement for me. All right, well, this has been Gaming Like It's 1979. Thank you so much. If you've made it to the end, you are a trooper. If there's interest, say something in the comments. Maybe I could go through and continue going through these puzzles. But, I mean, the fun of this game is playing it yourself. So that's not really my intention. I just wanted to show you what this was about and the kind of thought process that goes into this type of, dare I call it game programming? I do. Game programming. Thanks for watching.